Yeah, let us begin with a sort of assortment of topics, some of which were left out earlier and some of which complete what we already discussed. The first of these has to do with fractals. I gave an example of how we could find fractal dimensions for various sets. Here is another such example. Suppose I take all numbers between 0 and 1 on the unit interval and I write these numbers in ternary rather than binary. So I write each number, say the initial number that I start with, or any number at all x element of 0 to 1, I write this as 0 point a0, a1, a2 dot dot dot, where each of these digits is either 0 or 1 or 2. So I am writing everything down in ternary rather than binary. So the allowed digits for each of the AIs 0, 1 or 2. So clearly this A0 is the coefficient of 1 over 3 to the power 1, this is the coefficient of 1 over 3 squared, and so on and so forth. Then the question asked is, suppose I consider the set of all such numbers in whose ternary expansion the digit 1 does not appear at all. It is clearly a set of numbers and I would like to know what is the fractal dimensionality of this set. How would you go about this? So let S be equal to the set of all numbers in 0, 1 such that the digit 1 does not appear in the ternary expansion of these numbers. What is the fractal dimensionality or box counting dimension of the set? How would you go about this? What would you do? So I am not going to permit 1 to appear here. So this should be either 0 or 2, that should be 0 or 2, 0 or 2, and so on. Clearly I am a subset of numbers between 0 and 1 and I ask what is the fractal dimensionality.
1 by 3 into 1 by 3 square.
Yes, so how would you go about it? What would you do? Yes, but I would like to know what is the fractal dimensionality of this set. How would you go about that? Suppose A0 has a 1 there, then where would it be on this in this circle? Where would it be? So this is a 0 or a 2, and if it is a 0 this number is less than 1/3, so it is clear that the number would be so here is 0, here is 1, this is 1/3, that is 2/3. Yeah, it is exactly the middle third Cantor set, and it is not hard to find this because if this digit is 0 it is here, if the digit is 2 it is there, if the digit is 1 it is in the middle, and you are not going to allow A0 to be equal to 1. So this is cancelled here, and then if you look at A1 then it is again going to be the middle third that is erased each time, so it is going to be here or here and so on. You keep doing this forever, you get the middle thirds Cantor set. And what is the fractal dimensionality of the middle thirds Cantor set? Well, at each stage you take some interval of the preceding stage, you break it up into 3 parts and retain only the end 2 parts, and each of these is 1/3 the length of the preceding stage. Log 2 over log 3, so in this case D0 equal to log 2 over log 3, and it is the middle thirds Cantor set. So that is the answer. There is another famous regular fractal in 2 dimensions, there are many innumerable fractals. Another one is the so called Sierpinski gasket, and let me explain what its properties are. You start with a unit equilateral triangle in the first stage. So this is the and this goes over in the next stage to the following. You remove the triangle in the middle, so this portion is gone, and at the next stage you repeat this process. So this is already gone, that is a hole, and then there is another hole here and another hole here and another hole here, and you continue this ad infinitum. You are still left with a geometrical figure at the end which is riddled with holes, so to speak. This is called the Sierpinski gasket. What is the fractal dimensionality of this object? You start with this figure, the area here is, of course this is a 2-dimensional figure, so it is so in this case you would expect d naught to be equal to log divided by what? Do you think so? Do you think so? Yeah, it is equally divided. So you are getting rid of this and then you are getting rid of this, etc., and you are left with these little things which will then get riddled completely by holes. So what do you think is the fractal dimensionality of this object? You start with an area whose topological dimension is 2. So what is the fractal dimensionality here? So these are areas, mind you. Now what is the area of this figure? Okay. So what is the fractal dimensionality finally? Will it be greater than 1 or less than 1? So what do you get actually? You do not necessarily have to, you might get rid of the entire area. So there is no rule saying that you should have something which is greater than 1 or less than 1 or anything like that. So what happens in this case? How many pieces are you breaking each one into? But you are removing that, it is gone, so it is log 3 on top, and each of these is 1/4 of the earlier. So it is log 3 over log 4, which is a number between 0 and 1. It's not. You didn't say log 4 over log 3. Okay. So this is log 3 over log 4. Okay, my mistake. Okay. And so on. You can construct this in higher dimensions. I leave it to you as an exercise to tell me what the fractal dimensionality is if you did this in d dimensions, d spatial dimensions. In the next stage, for example, you take a tetrahedron which is a simplex in 3-dimensional Euclidean space, you take a tetrahedron and remove the middle by exactly the same construction, and you are left with tetrahedra at the corners of the original tetrahedron, and you can generalize this to d dimensions. So I leave you to tell me what d0 is in the case of a d-dimensional Sierpinski gasket in d Euclidean dimensions.
What will be the figure in the
You start with a tetrahedron, that will be the next thing. This would be the simplex, four-sided figure, it is a simplex, and now remove the middle, the solid object in the middle, and you are left with 4 tetrahedra at the ends.
What is the general shape?
The shape is self similar, that is at each stage you started with a triangle, it becomes smaller triangles. So you start with a tetrahedron, it becomes smaller tetrahedra. So you chop off the middle such that you have a tetrahedron at the corner here, at the corner there, at the corner there.
No, my question is the
Yeah.
original figure, how do you construct it in n dimensions?
Ah, what is the equation to a simplex in n dimensions? What is the equation to this tetrahedron? What would you say is the equation to this? It is a convex figure, it is called a simplex in d dimensions, and now you have to generalize the idea of this object, it is a rigid object here, to d dimensions as you go higher. Okay, I leave this as an exercise to you and we will give the solution subsequently. Okay. So these are all constructs, artificial constructs made in order to illustrate various properties of fractal sets. With the middle third fractal set, Cantor set itself, you can generate a multifractal. If you calculate it here, if you said, well, I just go through this construction at each stage and I associate a uniform measure with all these pieces, then all the generalized dimensions of this object would turn out to be just log 2 over log 3, nothing would happen. But if I start associating different weights with these objects, different probability measures, then in principle I can end up with a multifractal in which dq is not equal to d0 for all values of q. So this is often used in modeling, we will not get back to this right now. Okay. Let me now introduce you to a 2-dimensional map which has standard properties in the sense that it is hyperbolic, it displays chaos, and it gives you a little inkling of how this chaos arises. We already saw a 2-dimensional, the example of a 2-dimensional map, we saw the Baker transformation, which you recall was Baker's transformation. The Baker transformation or the Baker map. This started with xn and xn plus 1 was equal to twice xn modulo 1. So you stretched in this direction, and the yn plus 1 was equal to 1/2 yn if xn was less than or equal to a half, and it was half plus a half yn if xn was greater than a half in the unit square. And we saw this is an invertible map, so the number of pre-images for any point is equal to 1. We also saw that this map is chaotic and that the unit square in the xy plane gets completely scrambled up as you iterate this map, and that it has 2 Lyapunov exponents, one of which is log 2 and the other is a log half, and that the sum of the Lyapunov exponents was equal to 0, as it should be because this is a measure preserving map, and it mimics in that sense a Hamiltonian system in a very, very crude sense. Okay. Now the other famous map which does that is called the Arnold-Cat map, and it has got a fancy name, a more rigorous name, but let me just call it Arnold's cat map. And the map is as follows, it says xn plus 1 is equal to xn plus yn and yn plus 1 equal to xn plus twice yn, and both are modulo 1. Okay. Now let us see what this map does. In pictures, what it would do is the following. It would start with this thing here, x0 and y0. So it starts with a unit square in each of these variables, and then x1 is x0 plus y0 modulo 1 and y1, is of course x naught plus 2 y naught, again modulo 1. If you did not have the modulo 1, then what it would do is to do this, it would double in the x direction and it would triple in the y direction. Oh, not drawn it too well, so let me slightly smaller scale. So here is 1, here is 2, here is 1, here is 2, and here is 3. So what the map does is to take this guy here and distort it in this fashion such that the unit square becomes this. So this is what the unit square goes into this stage here, but you are supposed to do this modulo 1. So what you do is to cut out all these pieces and put them back into this square. What is the total area of this distorted square? That just depends on the determinant of this map. So if I call this map, well, let us call this map A. So what I have is xn plus 1 yn plus 1 is equal to this matrix 1 1 1 2 times xn yn, the whole thing is modulo 1 of course. The determinant of this matrix is unity, therefore it is measure preserving. We are guaranteed that the area of this object here is exactly the same as the unit area. And if I cut it and put it back here, then this map looks like it is on several pieces, but I could also pretend this map is on a unit torus, right. After all, once I say it is periodic, I could put this on a torus. I could simply say this, 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 etc. are all copies of this. So I could bring it back and put it on a torus, and then on a torus in which the circumference in this direction is 1 and the circumference in this direction is also 1. This object, whatever object you put here, remains continuous, you are not tearing anything. But the moment you say modulo 1 and you cut and snip and so on, it becomes disjoint pieces. So what will happen is that if you took some object here, some area here, that area would go over and get scrambled up, some of it would be here, some would be here, some would be here, etc. And since Arnold first drew a cat's picture and said this is the way the cat gets deformed, gets scrambled up, so what he did was to start with something which looks like this, and then that gets scrambled up as you go along. It became known as the cat map. Okay. However, there is serious purpose to this. Well, let us examine the properties of this map and see what happens. So my claim is that this map produces chaos, it actually scrambles it up completely, there is mixing and there is exponential sensitivity to initial conditions. The phase space is bounded, as we see, it is measure preserving, so nothing is lost, the unit square remains the unit square, but nearby points under iteration go arbitrarily far away, they become as big as the system size itself, and there is exponential sensitivity like the Baker map. Because you put this, because it is hyperbolic, and let us see what is meant by that. What are the eigenvalues of this matrix? So I have this matrix A which is equal to 1 1 1 2. What are the eigenvalues of this matrix? Well, it is clear lambda minus 1 times lambda minus 2, that is lambda squared minus 3 lambda plus 2 minus 1 plus 1 equal to 0. So lambda plus or minus is equal to 3 plus or minus square root of, so that is a 9 minus 4 is a 5 divided by 2. Those are the eigenvalues of this matrix. We will check what the eigenvectors are as well, and the eigenvectors would satisfy if u1 u2 is an eigenvector, then I apply this, and I insist that this be equal to u1 u2. So this implies that u1 plus u2 be equal to lambda times u1, the other equation does not give anything new. So it is clear that the eigenvectors for lambda plus, the eigenvector is if I choose u1 to be equal to 1 for instance, u2 is lambda minus 1 times u1. So this is equal to 1 and lambda minus 1, that is 3 plus root 5 minus 2, that is 1 plus root 5 over 2. That is the eigendirection. And for lambda minus, the eigenvector is 1 and then this is a minus sign here, 1 minus root 5, but since root 5 is bigger than 1, let me write this as minus root 5 minus 1 over 2. What is the significance of this number 1 plus root 5 over 2? It is a famous number, it is the golden mean, it is the golden mean. This number is the reciprocal of that number, as you can see. So we can plot what the eigendirections are now, and since this is a constant matrix, this is a linear map if you forget the modulo 1. Since it is constant, the Jacobian is the same everywhere at all points, and therefore this is what controls the expansion or contraction at every point. It is clear that there is an expansion in one direction and a contraction in another direction. If you go back to the original picture that I drew, it is quite evident that if this gets shifted out and then you end up with the sort of stretching in one direction in this fashion, if part of that parallelogram was cut and put here, so there is a sort of stretching in this direction and there is a contraction in the opposite direction. So if you quantify that, these are the eigendirections on which you have the stretching and the contraction. We can easily check out what it looks like. So here is the unit square, and let us look at this eigendirection. In what direction is this relative to this? What is this direction? This is the x direction and that is the y direction. This corresponds to x and that corresponds to y. So vector, unit vector with these as components, a vector with these as the x and y components would make an angle with the x axis which is the tan inverse of 1 plus root 5 over 2 divided by 1. This is about 1.618 or something like that, 1 plus root 5 over 2, right. We want the tan inverse of that. So that is some angle which is greater than 45 degrees, it is some crazy angle, it is 58 degrees or something like that. This is the direction. And the other guy, it is easy to check that these two slopes, the product of the two slopes is minus 1. So they are at right angles to each other. This is transverse in this direction, and that is going to be something like this. Not hard to check that this corresponds to an expanding direction and the other corresponds to the contracting direction. How do you come to that conclusion? How do you do this? After all, if I iterated this map n times, I get a to the power n acting on this x naught y naught modulo 1, right. Now how do I conclude that there is chaos in this system and that things actually exponentially separate out in at least one direction? It is the lambdas that control it, as you can see. And just like in the case of the one dimensional example of the Bernoulli shift, where I know that xn was 2 to the n x naught times modulo 1, and the Lyapunov exponent became log 2, because that factor 2 to the power n, if I take the log of it and divide by the initial separation, I end up with log 2 as the answer. If I divide by n and take the limit as n goes to infinity, I get the Lyapunov exponent. So that is exactly what we have to do here, except there are two Lyapunov exponents. And what are these two? What are the Lyapunov exponents for this map? No, no, the log of these things, the log of this, because you see, if I solve this map, it is evident that I am going to get something like xn yn equal to a to the power n x naught y naught modulo 1 always, that is putting it back in the unit square. But this guy here, if I took this matrix and diagonalized this matrix and wrote the elements down, the diagonal elements down, it would be controlled by the behavior of lambda 1 to the n and lambda 2 to the power n multiplied by two guys which are the do the diagonalization of this matrix, and then eventually the Lyapunov exponent will be given by log lambda 1 and log lambda 2. I call them lambda plus and minus, so let me. So these things could be written as e to the n log lambda plus, e to the n log lambda minus, and then this number here is a Lyapunov exponent. I am sorry, I used the same symbol lambda for the eigenvalue. I should have probably used mu here and then lambda for the Lyapunov exponent. Okay, so that is the reason for the confusion. Now what is log lambda plus? Yeah, so the Lyapunov exponent log 1 plus 3, sorry, 3 plus root 5 over 2. Is this positive or negative? It is positive, exactly. And the other one is log 3 minus root 5 over 2, and what is that? It is negative because this is the number less than 1, therefore it is the contracting direction, and we have also found the eigendirections, so this is negative. This direction contracts and this direction expands. This point here is like a homoclinic point because that is exactly the point. If I put this on a torus, it will keep coming round and round. So let us pretend that we are doing that. So since this is periodic modulo 1, it means that once you go out here, you are back here, you start here, and then this is what the unstable manifold is going to look like. So here you are, unstable, and you keep going round and round. So once you are there, you are going to be injected back here, and then parallel to this you are going to go off. Similarly here you are going to go off like this, and then you are going to come here, go off like that, and this will keep happening all the time. So there is at every point there is a transversal intersection. There is a transverse intersection. So what is happening is that you are on a torus, and along almost every point on the torus you end up with, except periodic unstable periodic points which we have not yet discovered, you have a contracting direction and an expanding direction. They are orthogonal to each other. So it is as if you have got saddle points everywhere. That is exactly what happened in the case of the Bernoulli shift as well. It is as if you have got separatrices everywhere because you have got these unstable periodic orbits at the rationals, things get thrown out on both sides, and that is exactly what happens here. Now because it is on a torus and because it maps the torus to the torus, it is called a toral automorphism, and because it is hyperbolic, no center manifold here, it is called a hyperbolic toral automorphism. And the name cat map is easier to handle, but this is not the only one. Any number of such maps could be constructed. You could put the integers down here such that the determinant is +1 and you end up with such an automorphism. It is a paradigm of chaos. It is exponentially unstable almost everywhere. and it has got an even dimensional phase space, it is measure preserving. So this was Arnold's example trying to mimic what happens when chaos sets in a genuine Hamiltonian system, and it happens because of the what is called the homoclinic tangle, and this gives you a sort of toy or caricature of what happens in such a system, that you have this expanding and contracting directions everywhere, the measure is preserved but it is chaotic with this Lyapunov exponent. Let us try to find what the periodic points are. Where are the fixed points of this map, and where are the periodic points of this map? How would we do that? Well, I need to know when this map leaves a point unchanged, and this is not so trivial to do, but let us see what to do about it. Now notice that under iteration, since we have xn plus 1 is equal to xn plus yn, before you do the modulo 1, if I start with these numbers between 0 and 1 and I go to xn plus 1, the maximum that xn can increase by is 1, it can't increase by more than 1. Similarly, yn plus 1 is xn plus twice yn. What is the maximum by which yn could increase before you do the modulo 1? 2, as we saw in the picture, right? You could add a 2 to the unit square, and then you had a square of a rectangle of height 3 and width 2. So it is clear that before you do the modulo 1, the largest that x can increase by is unity, and the maximum that y can increase by is 2. Therefore, if you have fixed points, if you have a fixed point, now what does it imply? Any fixed point of this map, of the nth iterate of this map, so I take a to the power n and I ask what about the fixed points of a to the power n? When n is 1 I get the fixed points of the map, when n is 2 I get the period 2 cycles of this map, and so on and so forth. So I am now trying to find all the periodic points and all the fixed points of this map. So it is evident that if x naught, for example, x naught y naught is a fixed point of this object, then it says xn must be equal to x naught plus some integer k which goes away in doing the modulus. Bad notation to use it like this. Suppose x naught is a fixed point, then after n iterations it would do this, where k can be 0 or 1 or 2 up to n, it can't be more than n, because after n iterations a point cannot increase by more than n, since in one iteration it can't increase by more than 1 before I do the modulus, before I do the modulo trick. Similarly, yn equal to y naught plus L if y superscript 0 is a fixed point of a to the power n, and so is x naught. If x naught y naught is a pair, is a fixed point of the map a to the power n, then you must have, after n iterations, this must go to this plus integer, where L equal to 0, 1, 2 up to 2n, because it could go right up to 2n, and then in the modulo 1 it goes away, that integer part goes away. Now this will help us find where are the fixed points of all of the map and its iterates. So let us look at the map, itself. So n equal to 1 implies that any fixed point must satisfy x equal to x plus k, where k can be either 0 or 1. But now I impose the modulo 1 condition. So what is the only possibility here? 0. So it must satisfy this. Similarly, y must be equal to, on the other side, y plus, and the only thing you can have here is a 0, implies under iteration what is the only fixed point now? This is the only fixed point. the origin is the only fixed point of this map, nothing else. Now I leave you to do the higher iterates, so do the first iterate a squared first and so on, and you discover some rational points would also be allowed, and then you do a cubed and so on, and it will turn out that all rational points are fixed points of this map or of its iterates. And this is not trivial to prove, not very difficult either. You can show that all rational points either are fixed points of the map, the only one is the origin, or lie on periodic orbits, like in the case of the Bernoulli shift. Now the rationals are dense everywhere on the unit square, the pair of rationals dense everywhere on the unit square, and those points would lie on periodic orbits. But tell me what happens to this line here, let us look at this guy here. The slope of this line 1 plus root 5 over 2, 1.618 or something like that, some irrational number. What is special about this line? What sort of points can lie on this line? Yeah, both x and y cannot be rational, right. So no rational pair can lie on this line, nor can it lie on all its subsequent iterates or on this. So these points will not pass through any pair of points, any points whose coordinates are rational, and yet they would densely fill up the entire square, but they would miss all the rational points. And that is what a chaotic trajectory would do, typical chaotic trajectory would do, but all the rational points are left out. Pardon me? The fixed points are all rational points. So a line like this is the unstable manifold and this is the stable manifold. This line does not pass through any pair of points both of which are rational, and so nor does any of its subsequent iterates. So this line here comes back and starts off here, and then it, after it goes here, it goes here, and then it comes here and goes here and so on. This thing will not have any point on it both coordinates of which are rational, and that would be generic, that is typical. So such lines, this line, the measure would be the total measure of this area itself, and the rational points form a set of measure 0. They are the unstable periodic orbits, and in its neighborhood you have these expanding and contracting directions. So it's a fairly complicated picture, but it's like a paradigm of chaos, Hamiltonian chaos in this case, because it's measure preserving. We saw a little bit about what irrationals do, and let me give you another illustration of a map, a simpler map, where you have this some properties of irrationals will emerge. Let me do that. I am not sure if I discussed this earlier. We go back to a one dimensional map where you have some interesting properties. Did I discuss the continued fraction map at all, the Gauss map at all? Let me do that now. So it gives you an illustration of the continued fraction map. This question was actually, this map was first considered, I do not know the exact history of it, but Gauss did very important work on this map, and it is the following question. In fact, the question that Gauss was interested in was the following. He said, suppose you take a number between 0 and 1, so I take an element x, element of 0 to 1, somewhere between 0 and 1, and I take its reciprocal, that is a number bigger than 1, I throw away the integer part, keep the fraction, I take its reciprocal, I throw away the integer part and keep its fraction, and then the question was, if I took a typical number and kept doing this and iterating this procedure, what is the probability that the number I end up with after a very large number of iterations is less than some given x, etc. So the question was, I start with a typical number between 0 and 1, take the reciprocal, throw away the integer part and keep iterating this procedure and ask finally what is the probability that the answer I have is less than some prescribed threshold x, which is between 0 and 1, and he found that this answer was very interesting indeed. It was proportional to log 1 plus x. This probability is proportional to log 1 plus x, and this excited him so much that he wrote a letter to Lagrange saying that he had found the solution to this problem. And what he did essentially in our terminology is the following. Let us see what this map is. So you start with the map which says that at the n plus 1 stage you take the reciprocal of xn and throw away the integer part. So it is minus 1 over xn, and this guy here is the integer part. So I use the square bracket to denote the integer part of this. And now the question is, is this map chaotic? If so, what is the Lyapunov exponent? What is the invariant density of this map, etc. This is the question we have to answer. What does the figure of this map look like? What does the graph of this map look like? So if I write x goes to f of x is 1 over x minus this, what does this graph look like? What does this graph look like? Pardon me? It is already going to be mod 1, so I start with x naught 0 1, I need to start with that. Okay. So I start with 0 and 1, between 0 and 1, I take the reciprocal, this is bigger than 1, I throw away whatever is the integer and I still have something between 0 and 1 and I keep doing this. So it remains between 0 and 1 automatically. Same thing, right? Same thing, right? Okay. Okay. So this tells you explicitly what you are doing. It will become clear why I wrote it in this fashion in a minute. What does the graph look like? In fact, why make a mystery of it? Let me tell you why I wrote it in this fashion. Instead of writing it as a binary number, a binary decimal, which is what we did for the Bernoulli shift, I can also write it as a continued fraction. So I can also write x naught as equal to 1 over a number bigger than 1, and in standard form any continued fraction can be written as an integer plus 1 over, once again an integer plus 1 over etc. forever, and in simple notation this is called 1 over a naught plus 1 over a1 plus 1 over 2 plus etc. This is notation for a continued fraction, so that you do not have to write this crazy diagonal everywhere. So these are integers, positive integers. What is x1? You take its reciprocal, then you have an integer plus a fraction and you throw this integer away, and therefore you have this, right. So this immediately implies that x1 equal to 1 over such 1 over a1 plus 1 over a2 plus. So you have lost information about this a0, it is clearly not invertible. Do you think the map is chaotic? Do you think it has fixed points? It has fixed points. Once we draw this graph it will become clear it has fixed points, but do you think these fixed points would be stable? No, they won't, because the slope of this map, this is some number, it is constant, each time it is a different constant. The slope of this map is 1 over x squared, the minus sign, and the mod of that is 1 over x squared, and since x is less than 1 this is always positive. So it is clear that this map has no stable fixed points, and its iterates are going to get only worse. So it is a candidate for chaos once again. There would of course be points which lie on periodic cycles, there would be points which are fixed points of this map and so on. What would the fixed points look like? For that we should draw this graph. It is clear that if I draw just 1 over x, then if I draw y equal to 1 over x, that is a rectangular hyperbola which passes through the point 1 1, but it actually does some crazy thing like this and goes off, and I start with a number between 0 and 1 here, and the graph is always bigger than 1, but I cut this and put it back, right. So as long as the initial point is to the right of a half, this is half, all I have to do is to subtract 1 to bring this piece and put it back here. So this map looks like this here. If the number is between 1/3 and a half, then I have to subtract 2 and bring it back and put it down here. So the map looks like this, a little steeper slope. If it is between 1/4 and 1/3, then I have to subtract 3, and therefore this map starts looking like this, and it is getting steeper and steeper as you go down. It has an infinite number of branches, right, and all of them have slopes in magnitude much bigger than 1 as you go to the left, and therefore all fixed points are unstable. But what are the fixed points? They are these intersections, these are all the fixed points, right. What does this point correspond to? So I would like to know what the fixed point there is for this map. This is the largest fixed point of the map here, and on this branch the map function f of x equal to 1 over x minus 1, because that is what I subtracted. So this fixed point implies that x is equal to 1 over x minus 1, or x times x plus 1 minus 1 equal to 0, x squared plus x minus 1 equal to 0, or x equal to minus 1 plus or minus square root of 1 plus 4, it is 5 over 2, and you want the number to be between 0 and 1. So the fixed point in fact is root 5 minus 1 over 2. So that is the only acceptable solution. That is the golden mean once again. What is its continued fraction representation? And that tells you why this number is the most irrational number of irrational numbers.
1 by 1 plus 1 by 1 plus.
Exactly, it is just 1 all the way through. You see what is happening here is that you want this number to satisfy 1 over x is x plus 1, or x equal to 1 over x plus 1, or 1 plus x. But now I substitute for x here as 1 over 1 plus x, etc., and keep going. So this is equal to 1 over 1 plus 1 over 1 plus 1 over 1 plus. In other words, all the AIs are 1, and now you see why it is so terrible to approximate this number by a rational number. Because if one of these AIs was very large compared to 1, you could truncate the number at that point and give a very good approximation to the number. This is what Ramanujan did when he took pi and did this, gave a continued fraction expansion of this such that the third or fourth of these guys was 293, which when compared to a fraction was much larger, and therefore he got an accurate estimate of pi to a very large number of decimal places by writing a very compact continued fraction expansion. So pi, although transcendental, although irrational, is not one of these very irrational numbers, quote unquote, which is in the sense that rational approximates are very difficult to find. very poor rational approximates approximate this very poorly, because these numbers are all comparable to each other, they are all equal in fact, and they are as small as they can be, 1. What is this number? What do you think it is? Yeah, it is exactly, it is just 1 over 2 plus 1 over 2 plus etc., because that number satisfies this. So this is the silver mean, this one is the golden mean, and this is the silver mean. What is the value of this number? What is this guy here? Satisfies this. So let us solve this. So it is x into x plus 2 minus 1 is 0. And the root that we want is this is twice root 2, so the root that we want is root 2 minus 1. No medals for guessing what this is. What is the continued fraction expansion of this? 1 over all the integers are 3. So much for the fixed points, and it is clear that all of them are unstable, the slope is greater than 1. So much for the fixed points. What about period 2 cycles of this map? You would want it to flip back and forth. It is quite clear that when you write the continued fraction expansion, you would want it to flip back and forth, right. So period 2 cycles are all numbers whose continued fraction reads like 1 over a plus 1 over b plus 1 over a plus. So perhaps you would have 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2 plus etc., that would be the leading, the very first, the largest period 2 cycle. It flips back and forth with 1 over 2 plus 1 over 1 plus etc., and so on. So you see the continued fraction expansion of the periodic orbits of this map have a very interesting simple expansions, and that is why it is also called the continued fraction map. That is exactly what it is, just as the Bernoulli shift was the binary shift, if you like. The Bernoulli map was a binary shift, similarly here this is the continued fraction map. Now let us try and find its invariant density. What was Gauss's result here and how did he get it, and its Lyapunov exponent. Well, the invariant measure would satisfy the Frobenius-Perron equation, so that would be rho of x equal to an integral 0 to 1 dy times rho of y times a delta function of x minus f of y. But what is this f of y? Yeah, this thing here would depend on where you are, right, but this f of y in general would be something like 1 over y minus some integer k, and all k's from 1 to infinity would contribute corresponding to all these branches. So if I did that, I end up with a summation from k equal to 1 to infinity of rho of, well, x plus k is y, so y is 1 over x plus k, so 1 over x plus k, that goes in here. Let us write this x minus, this is 1 over y plus k, and there is a summation over k. divided by the Jacobian of the transformation. The Jacobian of the transformation, when I take the modulus, it is just a 1 over this guy here. So what would it give you? 1 over x plus k the whole squared, because it is divided by 1 over x plus k the whole squared. So this is just x plus k. So let us write it properly, 1 over x plus k the whole squared rho of 1 over x plus k. Now this does not look like something which you are going to solve very easily, because it is a functional equation which is completely crazy, right, but this is what Gauss solved. In effect he solved this. So since we have, by hindsight we have Gauss to support us, let us write the solution down and see whether it works or not. So the solution that he had, I pointed out that he said it is proportional, the probability that the iterate after a long time is less than a certain number x is proportional to log 1 plus x, that is the cumulative probability. Therefore the probability density is the derivative of log 1 plus x, so it is 1 over 1 plus x. But you must normalize this to unity between 0 and 1. If I integrate this, I get log 1 plus x, right, and I put in the limits. At the upper limit I get log 2, the lower limit I get log 1, which is 0. So the normalization constant is 1 over log 2. Let us put that in and write our exact expression as this. This is the normalized density, and the question is whether this satisfies it or not. So the question we are asking is, the log 2 cancels out on both sides, it is a homogeneous equation. So the question we are asking is 1 over 1 plus x question mark equal to k equal to 1 to infinity 1 over x plus k the whole squared 1 over k plus, sorry, 1 over 1 plus 1 over x plus k. So you can see that this becomes x plus k on top and this becomes x plus k plus 1, and one of these factors cancels and you get this, and that is a convergent sum because it is going like 1 over k squared, so it converges faster than 1 over k. So the question is this true? This is the JE sum. What do you do next? Yeah, do partial fractions. You do partial fractions, so this guy here is indeed equal to 1 over x plus k minus 1 over x plus k plus 1, and of course terms the whole thing telescopes and only the first term would contribute and it will end up with just this. Only the k equal to 1 term, the left hand side survives, this one survives, and you get indeed 1 over x plus 1. So this is the solution, and we were assured that once you find a solution it is unique. So this is the solution. Of course please be careful, this sum here, this sum here is strictly equal to summation k equal to 1 to infinity, that I should not write it as a difference of two sums because each of them diverges. So as long as I keep the summation outside and the bracket inside the sum, this is fine, this is completely kosher, and indeed it is true. So the elementary, yeah, I do not know how Gauss did it, I am sorry, I should have read the history of this, I do not know how Gauss did it, I will look it up, I do not know how he did it, but I know he was sufficiently excited to actually write a letter and say he has found the solution. I do not even remember whether he wrote the letter to Laplace or to Lagrange or whatever, but certainly sent a letter to somebody in France on this. So now that we have rho of x, we can find the Lyapunov exponent of this map, Now what is the Lyapunov exponent physically measuring? It is in some sense measuring the average, the log of the average slope of this map, it is log mod f prime of x. So the average stretch factor it is measuring. Now the slope here at this point at x equal to 1 is 1 in magnitude, and everywhere else it is bigger than 1, and it is in fact tending to infinity as you come here. So the question is what is the average slope, but it has got to be weighted with that factor out there. So when you do that you get lambda equal to 1 over log 2 an integral from 0 to 1 dx over 1 plus x times log mod f prime of x, but f prime of x is minus 1 over x squared. So this is equal to log one over x squared, which is minus 2 log x. This is negative, but so is that, so the Lyapunov exponent is positive. Now what do we do with that integral? We can always look it up, of course we know it exists, it is not singular because the log is an integrable singularity, this is very harmless, the rest of it is not going to vanish at all. So the integral exists, there is no difficulty about it, but what do you think is the value of this integral? Unfortunately, because there is a sort of mixture, there is a rational function here and there is a logarithm here, it can't be done by elementary means, it is not a trivial integral, you can't do this by elementary means. So a little harder work is involved, it is a logarithmic integral, it gets related to the zeta function of 2, and the answer here it turns out to be equal to pi squared over 6 log 2. Okay. Because this integral, let me write that down here, integral 0 to 1 dx log x minus times 1 plus x. You can do this in several ways and show that this is indeed going to happen, one of which would be to expand this in a binomial series and try to collect terms and so on. The other would be to try to expand the log, but in either case this gets related to the following sum, which is zeta of 2, and that is pi squared over 6. So that is how the pi squared over 6 arises. This is defined, this is called the Riemann zeta function. And it is of argument 2, and it is finite. It is not hard to show that this number is pi squared over 6, it can be done in several ways, the simplest of which would involve contour integration. So since we haven't, don't want to get into that at the moment, but let me define what the zeta function is, it is useful information. Zeta of k is defined as summation n equal to 1 to infinity 1 over n to the power k. And to start with, you could ask what it is for positive integer values of k. Please notice if I put k equal to 1 it diverges, it logarithmically diverges. So k is 2, 3, 4 etc., and for 2 it happens to be pi squared over 6, for 3 it is fairly complicated, for 4 it is pi to the 4 over 90 or something like that, and so on. So simple expressions are available whenever this k is an even integer. When it is an odd integer, no such simple expression is available, but we know what it is numerically. This is called the Riemann zeta function because you can actually define it with any argument here. I could put an x here, and it is clear that if x is positive and greater than 1, then this converges even if x is irrational. In fact, since it is only the positive real part of x that matters, you could make it a complex variable, and all you need is the real part of z is greater than 1. it is an analytic function in the sense of analytic functions of a complex variable of this argument z, and in the z plane it is defined by this infinite series to the right of real z equal to 1. It stops converging when z is equal to 1. In fact, that series does not make sense anywhere on this line or to the left of it, but it turns out this function has meaning even to the left of it. It has a singularity at z equal to 1, it has a simple pole with residue equal to 1, and everywhere else it is analytic. So in fact you can define zeta of z not by this infinite series, not by this series, but by a different representation even to the left of it everywhere. The most important function, if you like, in analysis. But what we have here is zeta of 2, which coincidentally happens to be related to the Lyapunov exponent of the continued fraction map. There are deep connections here, there are reasons why this is so. And since I have digressed so far, let me also mention that the most famous, the most important problem in mathematics is the following, is the establishing of the Riemann hypothesis, which says that this function actually has zeros. At some points values of z it actually vanishes. Its proper definition to the left is done by what is called analytic continuation, that vanishes at some points, and it turns out you can trivially show that it vanishes at all the even negative integers like -2, -4, etc. It vanishes at all those points trivially. It also vanishes at points on a line perpendicular to the real axis, parallel to the imaginary axis, cutting the real axis at the point a half. So on this line on which z is equal to half plus iy, it vanishes at a large number of points, and it has got some symmetry properties on this. It vanishes at an infinite number of points on this line, and the Riemann hypothesis, one form of it, says that other than these trivial zeros, all the other zeros of the zeta function are on this line, and this has stood 150 years of as a challenge. Nobody has proved this so far. What is known is that there are an infinite number of zeros of the zeta function on this line. What is also known is that all non-trivial zeros with probability 1 lie on this line. You may wonder where probability comes in here, but it does. But what is not known is a proof which says there are no other zeros anywhere else. So people have numerically tried to find all the zeros on this. They found the first 13 billion zeros as of last October. They are all on this line. Yeah.
What's the measure of zeros for z equal to?
Now you could ask, what is the measure of the zeros here? What is the distribution of the zeros here? That distribution is related to the prime number theorem, which says that the number of primes less than a number x is of the order of x over log x. So the proof of the Riemann hypothesis on the number field, on the complex the numbers, would immediately solve a very large number of outstanding problems, so much so that it is taken to be a truth, and all those proofs rest on the truth of the Riemann hypothesis. But this has so far defied everybody. This is again the Riemann hypothesis, looks very specific to a very particular function and so on and so forth, but it is much more general than that, and it has got generalizations. So it is in fact the most important problem in mathematics. Now what is even more intriguing is that the distribution of zeros here turns out to be related to the distribution of energy levels for quantum mechanical systems which are classically chaotic. Now we do not fully understand the connections. So there are incredibly deep number theoretic connections between the zeta function, analytic number theory, chaotic dynamics, and quantum mechanics. And so much of this is still not known, maybe a lot of open problems, but certainly cracking any of these problems would be a major step forward. so I did not want to get into this, but incidentally there are all sorts of other relationships which lead to these things apart from the continued fraction map leading to this. For example, I give you two numbers and I ask you what is the relative probability that they are co-prime with each other, that they are two positive integers, and I ask what is the probability that they have a common divisor or they do not have a common divisor, and so on. That is related to 6 over pi squared again. So, and that is not hard to prove either, this is a fairly elementary proof for that. So there are all sorts of very interesting and deep connections, but what is intriguing is there are connections with real life, with the actual dynamics, dynamical systems, and the full reasons are not totally clear as yet. Okay, maybe I will stop here today. Thanks.